Thank you, Robin, for the kind introduction. So before diving into today's topic, I would like to take you briefly through the research center and about the research activities that we are currently looking at. So the Center for Biomedical and Biomaterials Research, CBBR, was created in 2011. And in December this year, it will be marking its 10 years of existence. The main research and innovation thrust of the research center is on the design and engineering of smart materials from locally available resources. It is also highly engaged in building intellectual capital through the training of postdocs and postgraduate students. It also offers consultancy services to industry through analytical services and also assists them in the uptake of nanotechnology. The head of the Center for Biomedical and Biomaterials Research, CBBR, is Professor Bao Luximan, who holds a personal chair in biomaterials engineering and nanomedicine. And the research at our center is divided into three broad categories. So we have nanofibrous scaffolds, hydrogels for molecule and cell encapsulation, and nanoparticle synthesis. I lead all research activities which is related to nanofibrous scaffolds. We also have a number of MPhil PhD students and postgraduate students who are working on a full-time basis at our research center. Now let us move to the main topic of today's lecture, which is the use of nanoengineered seaweeds for the treatment of diabetic foot ulcers. Type 2 diabetes is a worldwide problem, and one of the most important complications of type 2 diabetes is diabetic foot ulcer. In Africa alone, there is 19.4 million people who suffer from type 2 diabetes. And out of these 19.4 million people, 2.3 million of them suffer from diabetic foot ulcers. Now, diabetic foot ulcers, they are chronic wounds that occur in the lower extremity of the limbs. And they are very slow healing in nature. They can take months or even years to heal. And in most cases, they do not heal at all, leading to amputations. It is estimated that 15% of people who suffer from a diabetic foot ulcer will experience an amputation. Because of the slow healing nature of diabetic foot ulcers, and also because of the fact that they lead to amputations, these kind of wounds, they add significantly to the economic burden of a country. In Africa alone, the total economic burden due to diabetic foot ulcer is estimated to be around 11 billion US dollars. Commercial products which are available to treat diabetic foot ulcers are very expensive. And on average, it costs around 1,000 euros to treat a single diabetic foot ulcer. Therefore, this is not affordable for the African continent, and there is an urgent need to develop cheap and affordable materials which could be used to treat diabetic foot ulcer in Africa. So what we are proposing is the use of nanoengineered seaweeds to treat diabetic foot ulcers. More specifically, we are proposing to use nanofibers in the form of blend fibers consisting of a seaweed-derived polymer in combination with another biodegradable polymer to treat these types of chronic wounds. Now, the concept of tissue engineering to regenerate skin is a fairly simple concept where we need raw materials. So the raw materials are the skin cells and the scaffold. The skin cells are then placed onto the scaffold, and then the cell-seeded scaffold is placed in a bioreactor where they have the appropriate condition for them to grow and eventually give rise to the new tissue, which in this case will be skin. Now, in tissue engineering, the scaffold plays a crucial role. And in fact, it is the scaffold that will determine whether the tissue engineering process is going to be successful or not. In vivo, or in the human body, the cells, they are located in a very complex and dynamic microenvironment which is known as the extracellular matrix. The cells, they are constantly communicating with each other, but also with the extracellular matrix components. The extracellular matrix consists mainly of proteins, such as collagen and elastin, but also consists of specialized proteins such as glucosaminoglycans. The seaweed-based polymers that we are looking at, their structure resembles closely that of the glucosaminoglycans. And therefore, when we are using the seaweeds, we are able to trick the cells into thinking that they are in their native microenvironment. So in the first part of our study, we fabricated blend nanofibers consisting of a seaweed-based polymer in combination with a biodegradable polymer, which in this case is polydioxanone, which is here abbreviated as PDX. We were mainly concerned with two different types of seaweeds, namely red seaweeds and brown seaweeds. From the red seaweeds, we extracted the polymer kappa-carrageenan, which will be abbreviated as KCG in the next slides. And from the brown seaweeds, we extracted fucoidan, which is abbreviated as FUC. So we basically fabricated blend nanofibers consisting of PDX and KCG, or PDX in combination with fucoidan. And the ratio of PDX to the seaweed-derived polysaccharides were varied, such that we had a range of different compositions. The blend nanofibers were characterized in depth in terms of their physicochemical properties. And we can see from the images on the right-hand side that all the fibers, they were very smooth and there were no surface protrusions. Now, if we look closely at the scanning electron microscope image shown on the lower right-hand side, we note the presence of a second component for the fucoidan-containing fiber. And this is very likely due to the presence of fucoidan on the surface of the fiber. The wound healing cascade consists of three overlapping stages, namely the inflammatory phase, the proliferative phase, and the remodeling phase. In the inflammatory phase, we're going to have an increase in blood flow, and macrophages are going to be activated and they're going to migrate to the site of the wound. After the inflammatory phase, we're going to have the proliferative phase, where we're going to have proliferation and migration of fibroblasts to the wound site. And at the same time, we're going to have proliferation of keratinocytes to the wound site, and this is going to be followed by migration of endothelial cells at the injury site. And in the last stage of the wound healing process, we're going to have collagen synthesis and matrix reorganization. And at the same time, we're going to have angiogenesis, which is basically the formation of new blood vessels. And also, fibroblasts are going to be involved so as to reduce superficial contraction and scarring in the wound. We therefore tried to investigate the potential of the fabricated scaffolds in each of the different phases in the wound healing cascade. So first of all, we looked at the inflammatory phase. So we seeded firstly mouse macrophages on the scaffolds, and we took scanning electron microscope images of the cells after 48 hours. The images shown on the left-hand side indicate that as we increase the polysaccharide content, the cells, they became more flattened in shape, and also they became more smooth. And we analyzed the cell area of the macrophages on the different scaffolds, and we found that as we increased the biopolymer content, the cell area was also increasing, irrespective of whether the polysaccharide was kappa-carrageenan or fucoidan. In the next step, we stained the cells in terms of their nucleus and cytoskeleton. So the image on the upper right-hand side shows the fluorescence microscope image of the macrophage cells. In blue is the nucleus, and what is stained in green is the cytoskeleton of the cell. We tried to quantify the actin edge intensity of the cells, and we noted that the actin edge intensity increased as we increased the biopolymer content. And overall, these results indicate that both kappa-carrageenan and fucoidan addition to the scaffold favors the polarization of macrophages to the M2 phenotype, which is basically the pro-healing or anti-inflammatory phenotype. We also tried to look at the behavior of the scaffold in the proliferative phase by seeding fibroblast cells on the scaffold. We tried to quantify the number of cells that were growing on the scaffolds after 7 days using MTT assay. And the graph, which is shown on the left-hand side, gives a summary of the results that were obtained. So overall, we could conclude that the cells proliferated very well on all the scaffolds, and they maintained good viability. And this was in line with scanning electron microscope images, where we could see that the cells completely covered the surface of the scaffold after 7 days. Another aspect which is very important in the proliferative phase is the migration of cells so as to close the wound. We therefore carried out in vitro wound scratch assay to look at the migration potential of fibroblasts using the seaweed-derived scaffolds. And the image on the right-hand side basically show how the wound was closing and how the cells were migrating into the in vitro wound site. And we found that all the samples, therefore the positive control TCPS, the kappa-carrageenan containing scaffold, and the fucoidan containing scaffold, they all favored migration of cell into the wound area. But if we look closely at the three images, we can see that the fucoidan containing scaffold promoted the migration of fibroblasts to a much higher extent compared to the remaining two samples. In the remodeling phase, a very important process which occurs is angiogenesis, which is basically the formation of new blood vessels. For any tissue or organ to be viable, we need to have a good supply of blood, oxygen and nutrients, and also removal of waste products. And all this happens through a good blood vessel supply. Therefore, to look at whether the scaffolds were promoting angiogenesis, we seeded endothelial cells on the scaffold. And the graph on the lower left-hand side indicate that the cells proliferated very well on all the scaffolds, and the cell number remained practically the same on all the different scaffolds, irrespective of the biopolymer content and on the nature of the polysaccharide. The scanning electron microscope image was in line with the MTT results, where we noted a very high number of cells on all the scaffolds. And if we look closer at the scanning electron microscope image, we noted the presence of lumens in the scaffolds. Therefore, the cells were rearranging so as to form lumens, and this indicates the good angiogenic potential of the scaffolds. We also looked at whether the scaffolds could be used to grow and to support the growth of induced pluripotent stem cells. So briefly, we fabricated embryoid bodies consisting of around 2,000 induced pluripotent stem cells. So as we can see from the optical image on the right-hand side, we note that the embryoid bodies were very uniform in shape, and the average diameter of each of those embryoid bodies was around 343 micrometers. These embryoid bodies were then seeded onto the nanofiber scaffold, and after 24 hours, we performed live and dead staining on the cells to see whether the cells were still viable or not. And these are the results that were obtained after the live and dead staining. So basically, all the live cells are stained in green and the dead cells are stained in red. Therefore, we can conclude that most of the cells were viable on the scaffolds, and there were very few dead cells on the seaweed-derived polysaccharide-based scaffolds. Because the scaffolds that we are fabricating are intended for human applications, we have to ensure that these scaffolds are non-toxic and biocompatible. Therefore, we carried out in vivo biocompatibility studies where the scaffolds were implanted in Wistar rats. So basically what we do is that we create subcutaneous pockets on the dorsal region of the rats, and then we implant 3 layers of scaffolds in each subcutaneous pocket. The 3 layers of scaffolds were labeled as exterior, middle, and interior. So the interior layer of the scaffold was the layer that was in contact with the muscle layer. And the exterior layer of scaffold was the layer that was in contact with the skin. The rats were then followed over a period of 4 weeks, and during that time period, we look for any signs of inflammation such as redness or swelling, and we also note the weight of the animal. At the end of the study, that is, at the end of 4 weeks, we took out the scaffolds and we analyzed the scaffolds under the scanning electron microscope. And we found that all 3 layers of the scaffolds were completely covered with cells, and this therefore indicates that the cells could easily infiltrate in between the 3 different layers. We also took out a piece of the tissue at the subcutaneous pocket site, and we analyzed it in terms of histological analysis. And the image on the upper right-hand side show that for all the 3 scaffolds, we had the presence of a fibrous capsule that was formed around the scaffolds. But if we look closer, the thickness of the fibrous capsule varied depending on the nature of the scaffold. Therefore, if we look at the graph on the lower right-hand side, we can see that the fucoidan-containing scaffold led to the thinner fibrous capsule in comparison to the kappa-carrageenan-containing scaffold or the pure PDX-containing scaffold. Therefore, overall, we can say that the incorporation of fucoidan leads to better in vitro and in vivo cellular response compared to kappa-carrageenan. In the second part of the study, we fabricated a second class of blend nanofibers, still consisting of seaweed-derived polymers, but this time in combination with another biodegradable polymer, namely PHBV. Now, PHBV stands for polyhydroxybutyrate valerate, and it is a special polymer because it has piezoelectric property. Now, a piezoelectric material is one that produces a voltage or a current when subjected to an external force. When cells are seeded on a scaffold in vitro, the cells are going to colonize the scaffold, and the cells exert a mechanical force on the scaffold. This leads to microdeformations, which produces piezoelectricity. In the human body, there are different tissues which are piezoelectric in nature. These include bone, cartilage, ligaments, and even skin. Therefore, we hypothesize that the use of a piezoelectric polymer in combination with the seaweed-derived polysaccharides are going to further improve the wound healing process and accelerate the skin regeneration. Therefore, to test our hypothesis, we performed in vivo wound healing studies where we compared the performance of different seaweed-containing scaffolds over different time periods. So the wound healing study was carried out over 21 days, and we took photos of how the wounds were closing over time for the different scaffold groups. So scaffold 1 corresponds to the negative control and scaffold 2 corresponds to the positive control. Now, if we look closely at the first 2 scaffolds, we see that the wounds did close after 21 days, but we had the formation of a scar. In comparison to the scaffold treated groups, we do not see the formation of scar at the end of the wound healing process. And if we look even closely to scaffold 5, we see that there is no scar formation at all right at the start of day 13. Now, after the wound closed completely, we took out a small tissue at the wound site, and we performed histological analysis. So the tissue was stained in terms of Mason's trichrome, and we quantified different parameters such as the epidermis thickness, the dermis thickness, the granulation tissue area, as well as the global healing index. In general, a high global healing index together with a small granulation tissue area corresponds to good overall healing. Therefore, if we look closely at the table on the right-hand side, we note that scaffold 5 led to the lowest granulation tissue area and the highest global healing index, which indicates that this scaffold led to the best performance. And scaffold 5, if we look at the table here, scaffold 5 corresponded to PHBV fucoidan. Therefore, the scaffold contained fucoidan in combination with the piezoelectric polymer, which confirms our hypothesis that the fucoidan, when in combination with a piezoelectric polymer, leads to better or accelerated wound closure. To conclude, we successfully fabricated blend nanofibers consisting of seaweed-derived polymers, and we showed that these blend nanofibers could promote fibroblast migration and proliferation. They promoted the macrophage polarization towards the M2 phenotype and also promoted endothelial cell proliferation, as well as supported the growth and proliferation of induced pluripotent stem cells. And most importantly, in vivo wound healing studies showed that there were no scar formation, and also the blend fibers accelerated the wound healing process in contrast to the negative control or to the remaining positive samples. Finally, I would like to thank the head of the research center where I work at, and also our research group leader, and also all colleagues who work at the same research center. And special thanks to the funding agencies, in particular, the University of Mauritius and the Mauritius Research and Innovation Council, the L'Oreal UNESCO Foundation and the Alexander von Humboldt Foundation for funding my postdoctoral fellowship. And of course, a special thank you to Siwa, who is our close collaborator for in vivo testing. Thank you.
Dr. Goonoo, that was really very, very interesting indeed. It's a little way from my personal expertise, but I am particularly interested in some of the nanomaterials aspects. So I'm going to start by asking a question about the morphology of the scaffolds and the morphology of the blood vessels that form in the last stage of wound healing. Is there a relationship between those different morphologies?
Yes, so thank you for the question. It's a very good question. So firstly, let me answer the first part of the question, which is about the morphology of the scaffolds. So as you have seen in the talk, all the scaffolds, they are blend fibers, so they are nanofibers in nature. And the reason why we chose the nanofibrous nature of scaffold is to be able to mimic the native microenvironment in which cells are located. So if we recall in one of the slides, we saw how the extracellular matrix looked like, and we see that the cells, they are surrounded with polymer fibers. So that's why we chose a scaffold, which is fibrous in nature, so as to be able to mimic closely the microenvironment in which cells are located. Now, the nanofibers, they are also quite interesting in the sense that they offer, for example, a very easy way of modifying those fibers so as to attach functional groups to them, so as to make them more biocompatible, for example. And also using the process of electrospinning to make the nanofibers, we can choose a wide range of polymers so that we can convert them into nanofibers. And another interesting aspect of nanofibers is that they are 3D in nature, and they're also porous, which means that they can absorb wound exudates in the case of diabetic foot ulcers. And the second part of the question about blood vessel formation Indeed, we do observe a difference in terms of how the endothelial cells behave on the different scaffolds. What we noted was that the endothelial cells, they preferred nanofiber scaffolds with small fiber diameters. And so far, we have only looked at 2D cell cultures, therefore cultures of culturing the cells on the scaffolds in terms of a 2D nature. And we have not looked at how the cells were organizing in 3 dimensions. But this is something that we are planning to look at in the future. And I'm sure that we will have very interesting results with regards to the different types of polysaccharides and the rearrangement of the endothelial cells on the different scaffolds.
Okay, so from sort of my perspective, again, of not being an expert here, so this means that these scaffolds are bioactive as well as being biocompatible, is that right?
Yes, it's correct. So those polysaccharides that we used, like kappa-carrageenan and fucoidan, they possess some special functional groups on the backbone, which makes them biocompatible and also bioactive. Therefore, the cells like those functional groups, and they proliferate very well on those scaffolds. So it's similar to, it resembles, in fact, the proteins which are found in the extracellular matrix.
Okay, I think I'm starting to understand. So if we were to come back in, say, 3, 4, 5 years' time after this process had been used, would the original scaffold material then have been be absorbed by the body and replaced by completely new cells, or will that scaffold always be there?
No, so actually the scaffolds, all the scaffolds that we are looking at, they are biodegradable, which means that they will be absorbed away over time. So there is something which we look at there, which is very important, is the biodegradation rate of the scaffold. So
Right.
in the tissue regeneration process, for example, in this case, we are looking at skin repair of diabetic foot ulcers. It's very important to match the biodegradation rate of the scaffold with that of skin tissue regeneration. Therefore, what happens is that as the new tissue is being formed, the scaffold is slowly dissolving away, so that at the end of the wound closing process, there is no scaffold left at the wound site. So it's only the tissue which is formed, the new tissue formed, which is present.
Oh, wow. So does that mean that, looking again 10 years time or something, that different people will get slightly different scaffolds to match their body types or the way their bodies behave? Is that possible?
I actually doesn't really depend on the individual, but it depends on the tissue that you want to regenerate. For example, skin is going to take, let's say, 1 month to heal, but bone will take much longer. So we design the scaffolds according to the tissues that we want to regenerate.
Right. Okay. So you're going to be busy looking at all sorts of scaffolds for a long time. That's really very good. Now, I know we've got a little bit of time to have a chat, and I this seems very unfair to everybody else and I can see that there are some questions starting to come up. But before we go to that, I wanted to ask you a little bit about, you've talked to us about your research centre, and so I think I understand that. But I'm thinking perhaps about the wider networks that you work with, perhaps particularly in Africa. Can you tell us a little bit about those, please?
Yeah, so I form part of the young affiliates of 2 African organizations, namely the African Academy of Sciences and the World Academy of Sciences. Now, the African Academy of Sciences is a non-political and non-profit organization. And its main aim is to promote and recognize scientific excellence in Africa. So each year, it selects through a peer review process early career researchers, which it's going to integrate in its young affiliates program. Now, what happens as a young affiliate is that you are able, for a period of 5 years, to receive career support and also mentorship from recognized researchers worldwide, and you're also able to access different networking opportunities, which helps the early career researchers to progress in their career. And the World Academy of Sciences, just like the African Academy of Sciences, has the same aim. But in addition, it helps to promote North-South and North-North collaborations. And it also offers several fellowships for postdocs and PhD students, and also several conference possibilities to attend conferences, and also different prizes for PhD students and postdocs. And all this is done just to recognize African researchers who are working in this in science in general.
Well, I think that's a really useful comments, actually, because there's an awful lot of people listening to this this evening or this morning or wherever they are on the planet. And what you've done there is given them some opportunities to start to develop how to interact better and more fully with other people in African institutions. So that, I think that's a really important sort of comment that you've made there. Now, I wanted to sort of go back to some of the sort of science that you're doing. And I'm going to start including some sort of questions that we have. So we've got one here about how do you extract the polymers from the seaweed? Can you tell us a little bit about that process?
I'm sorry, can you repeat the question?
Sure. How do you extract the polymers from seaweed?
Yes, so the extraction process will depend on the polymer that we want to have at the end. For example, if you're starting with red seaweed, you want to have, for example, carrageenan, and if we start with brown seaweeds, you want to have fucoidan at the end. So the extraction process is going to be different. But overall, the process that we work with is using the alkali process and then precipitation in an alcoholic condition. So it's a very simple process. And the yield also is dependent on the polymer that we are extracting. For example, for carrageenan, the yield is quite high. It's up to 70%. But for fucoidan, we have a lower yield, which is less than 20% sometimes.
Do you think that will impact on the industrialization of this process?
Yes, certainly. That's why we have been concentrating on carrageenan up to now, but we have seen that fucoidan shows much better properties. So what we're trying to do now is to look at other methods of extracting fucoidan from the brown seaweeds, and we are looking at microwave-assisted extraction of fucoidan right now.
Okay, that's quite interesting. It actually follows into a question that Jakub has asked. That was the previous question was by Professor Than, by the way. And Jakub says here, what are your main goals with the process for the next 5 years?
Okay, so in terms of my goals is to optimize the extraction process so that we have better yield, especially for fucoidan, and to minimize the use of solvents as much as possible, because when we are moving up to a large scale, we want to reduce the cost as well. And we are looking also at environmental friendly processes, which will be easy to scale up. And as we have seen through the presentation, we have already performed animal studies. So the next stage will be to perform in vivo diabetic wound healing studies, because the studies that I've shown were not diabetic wound healing studies, they were just normal wound healing studies. So this will be the next step. And then after the diabetic wound healing studies, we are hopefully looking forward to being able to carry out clinical trials on human patients in Mauritius. And then hopefully be able to come up with the first Mauritian nanotechnology product in terms of wound care for diabetics in their local continent.
Okay, that really is very, very interesting. And I'm sorry, I'm not, to the people who are asking questions, I'm not doing this in a particularly good order, I'm afraid. I apologize. But I think actually Elias has asked a question here, which I think follows on very nicely for that, is when will skin regeneration therapy be available for patients?
Actually, skin regeneration therapy is already available. So we already have quite a few commercial products on the market. But the problem with these products is that they are very expensive. And if we look at the African context, the cost is something which not everybody can afford. And the second thing is that the logistics which are involved in storing those products and in shipping those products to the African continent is not something which is feasible for Africans. So that's why we are looking into alternatives to make cheaper skin regeneration products for the African continent. So the commercially available products right now are mainly collagen based. So that's why they are very, very expensive.
Okay. I suspect, though, that the range of different morphologies and things that you have available to you from the natural products may well actually make a rather better therapeutic outcome. Of course, that's what you're trying to do, isn't it? Which is, and also why you've got this sort of prize. Now, there is another question, and I apologise. This is from Susan Graeff, and she said, thanked you for the seminar as well. I should say that when the nano-engineered seaweed is made, and it's phyllosilicates used. I'm not quite sure whether or not there is a typing issue there. So if Susan would like to retype that if that isn't quite right, but does that make sense to you?
No, I'm sorry, I didn't quite get the question.
Oh, it's polysilicates.
Okay, no, we do not. Yeah, I got it now. Thank you. So in response to Susan's question, no, we do not use any silicates in the scaffolds. It's just biodegradable polymers for the reason that we want the scaffold to dissolve away when the tissue is regenerated. So we only make use of a polyester in general to give mechanical strength to the scaffold, and we use a polysaccharide to give this bioactive component to the scaffold. And sometimes we add in small amounts, less than 5 weight %, we add natural molecules to help with the different phases of the wound healing process. For example, we could add curcumin, for example, to help with the inflammation part. And we have other molecules that we are looking at to help with each aspect of the wound healing phase. But the main component of the scaffold remain a biodegradable polyester and the polysaccharide.
Okay. It almost makes me want to ask you the sort of question. When you first started out, because there's so much polymer chemistry here that you are you have your fingers on all that polymer chemistry. I can see you really understand it thoroughly. Did you start off as a polymer chemist, or did you start off in a chemistry degree, or?
Yes, so I started with an undergraduate degree in chemistry, and then I specialized and did a postgraduate degree and studies in polymer chemistry. And then in my postdoctoral years, I further specialized to learn more about cell biology, biomaterial science, engineering, material science, and things like this.
Okay, so you came at it in that direction. Thank you. So Jeffrey Greenspan has asked a few questions here, and I'm going to start with this one. And he's saying, do different seaweeds differentially promote different phases of wound healing? So I think what he's getting at here is such that a mixture of different seaweed extracts provide optimal wound healing. Yeah,
so we actually, yes, it is. We have observed this, but not with capacaragidin and fucoidin. But from the slide that I have shown, we see clearly that, for example, in the inflammatory phase, both polysaccharides, they do not behave in the same way. So it is very, very possible that for the other phases as well, the two polysaccharides behave very differently. But we do not observe significant differences for these two polysaccharides that we have looked at. But these were very preliminary results. We have to look into more in depth in terms of 3D cell cultures, especially for the proliferative and remodeling aspects. But we are sure that this is going to be something really interesting that we need to look at.
Okay, yes, and he'd asked a previous question actually, do some seaweeds promote one characteristic but not the other? And I think you've addressed that in your answer then, haven't you? Now, Professor Than has then asked another question about going back to the issue of extraction of the scaffold materials. And he's asking about the purity of the materials. How do you think about the different purities of your scaffold materials?
So in terms of the polyesters, we buy the polyesters, so it's over 99.9% purity. And concerning the extracted polymers, they are also 98 to 99% pure.
Okay. It does, because these are natural materials, of course, you must get quite a lot of variability from the different seaweeds, perhaps even across different periods of time. Although I guess in Mauritius, you don't have very big changes in sea temperatures, or do you, across the year?
No, we don't have big changes in temperature, but during the extraction process, by controlling time, for example, and temperature and concentration and other things like this, we are able to extract a specific polymer with a specific molar mass.
And actually, Connie has asked a question here, which goes again, following on for the same thing. Would the seaweed type need to be adjusted for people who require or want skin regeneration, but are using medications such as antibiotics to treat other medical problems?
In terms of adjustment, I'm not sure what the latter means. What I want to add is that if a person is taking antibiotics, for example, there is the possibility of including those antibiotics in the scaffold and then having it released slowly over time so that the person doesn't need to take the antibiotics orally. And if, for example, that person is taking antibiotics for an infection occurring at the wound site, then it's even better because the release is occurring at the local site of the infection, and it's going to be a more optimal treatment compared to taking the antibiotics orally.
Yes, I think that's a really, really interesting point here. So your materials are going to have an incredible variety of different jobs to do for these sorts of wounds. I mean, you've talked about diabetic wounds in particular. Do you see other types of wounds, other types of issues being able to be addressed using these sorts of materials?
Yeah, so another aspect of my research deals with the fabrication of scaffolds for cancer regenerative purposes. So what we mean by cancer regenerative medicine here is basically when we consider a solid tumor and that person has the solid tumor removed, there is a wound which is created there. Now, we are all aware of the fact that the cancer can come back again. So we have recurrence and relapse. So what we're trying to do is, through the design of those scaffolds, we want to have the scaffolds to have two main purposes. So the first purpose is to act on the cancer cells so that to prevent the cancer cells from growing back again. And at the same time, promote the healthy cells to grow and proliferate and close the wound. And so what we need is therefore to have a balance in the scaffold between promotion of healthy cells and killing of cancer cells. So this is something which is very, very tricky. And we have been looking at this for over 4 years now, and it is something which is really complicated. And right now, in terms of solid tumors, we are looking at pancreatic cancer and melanoma.
Okay, and those.
And we have been considering those polysaccharide-derived scaffolds for those purposes as well. And this aspect is still under investigation, but I can say that the results have been very interesting.
Okay, that really is interesting. So there's a difference between the way that a cancer cell and a healthy cell interact with the scaffold. Any idea why?
So it has to do with the environment that the cells like. For example, for melanoma cells, we observed that fucoidan has a higher cytotoxicity towards melanoma cells. It is also cytotoxic at high doses to healthy cells. So the trick is to balance, to have the fucoidan at the right concentration so that it is able to kill the cancer cells, but not kill the healthy cells. And at the end, help to promote the cells to, the healthy cells to grow. So it's having the right dose, which is the trick in getting those scaffolds to work for cancer regenerating medicine.
That really is very interesting. Fine. You're not going to have a shortage of things to do, are you? You really are going to be a very busy person indeed. Rachel McDonald has asked a question. She said, how do the seaweed scaffolds compare to commercially available products in promoting wound healing in the animal studies? Are the seaweed products more effective than collagen products, for example?
Yeah, so this is a very good question, and I must say I was expecting this question. So yeah, so in terms of comparison of the performance, I must say that they are both, the performance is comparable for both commercial and our fabricated scaffolds. And if we look at the animal studies, what we note is that the wounds treated with our fabricated scaffolds take longer time to heal compared to the commercial collagen products, for example. But this is not a bad thing. Why? Because when we look at histology images and we look at the cross-section of the tissues of the wound that was closed, what we note is that for the commercial product, the wound closed, but it was only superficial. So you have only superficial wound closure, but inside it was hollow. So there was still tissue which was not filled inside the wound. In comparison to the wounds which were treated using our fabricated scaffold, the tissue started to grow from the inside and then completely closed the wound. So there was no hollow space inside the wound. So one of the main complications or main issues that we observe with diabetic foot ulcer is that the wounds, once they have closed, they reopen with time. And this is why it reopens with time, because the wound is not completely closed. It's closed only superficially. So it's very important to have the tissue grow from within the wound and then close also at the surface. So this is something that we are very happy about, that even though our scaffolds take slightly longer time to heal, the wound or the new tissue that is formed is much better compared to the new tissue that is formed using commercially available products. And the second thing is that the wounds, when they are treated with the seaweed-derived polysaccharides, they do not lead to scarring. And this is something which nobody would like, that is having a scar after you have had a wound.
Oh, that's interesting. Oh, that is a tremendous advantage, actually. Okay. Huh. So Jeffrey Greenspan's come back and he's asked whether the scaffolds promote cytokine production.
Yes, they promote cytokine production, especially in the inflammatory phase. And for example, fucoidan promotes both pro-inflammatory and anti-inflammatory cytokines, and the same for kappa-carrageenan polysaccharides. And depending on the concentration that the polysaccharides are being used, the concentration of cytokines that is going to be produced is also going to vary. But if we compare, for example, both polysaccharides at the same concentration, we note that the fucoidan-containing polysaccharide will cause the formation of anti-inflammatory cytokines compared to kappa-carrageenan. So it promotes the macrophages via the secretion of cytokines towards the pro-healing phenotype.
Okay, so that really is part of the advantages on the compared to commercially available products at the moment, in fact. Okay, that is interesting. You talked a little bit about piezoelectric polymers and how, you know, a mechanism by which that might play a role here. And I have to say I'm quite interested in that, in piezoelectric materials in general terms. But if you apply an external electric field, then could you change or use that piezoelectric behavior as part of the therapeutic process? Is there something that you could do using the piezoelectric nature of these materials?
So the goal or the aim of using the piezoelectric polymer is so as to not be dependent on an external electric supply or power supply. So we don't want to have to add an electric current or a voltage to provide this piezoelectric property. So for these piezoelectric polymers, for example, if we apply this to an animal, for example, through the motion of the animal, this is going to cause micro deformations on the scaffold, and this is in itself is going to bring about the piezoelectricity, and this is going in turn to trigger cellular response and cause cell proliferation and wound closure, as we have seen over time.
Okay, but there is a possibility that if you did apply an external electric field, you could get an additional effect, in fact, on these materials.
Yes, it's possible that we can have an additional effect, but this is not something that we are looking at because it's going to further complicate the process, and we want to have something which is very simple and very easy to apply in the in clinical settings.
Yes, no, quite right. Keep it simple. It's complicated enough as it is. John Percival's asked, how relevant is this technique to burn treatment?
It's as effective as for diabetic foot ulcers. So all the scaffolds that we have designed for skin regeneration can be applied for burn wounds as well, but we have not tested them on in vivo models yet. We have tested them only on ex vivo models. And so far we have seen very good results. So we are also, this is another direction in which we are planning to go and look at in terms of burn wounds. But we are very happy that the results have been very positive for both burn wounds and diabetic foot ulcers as well.
You're doing a tremendous amount of work. How can you remind us, how big is your group now?
So the research center that I work at currently, we are a total of 15 people. So we have 2 permanent staffs, and we have 10 postgraduate students and 3 research assistants. It's not a very big group, but we're doing the best we can.
Well, you are doing very, very well. You just won a prize. I mean, I think that that says it all, does it not? But yeah, I think you must all be working every hour that's possible to have created so many absolutely fascinating results. So we are actually getting towards the end of our time here today. So I'd like to encourage, if there's anyone who wants to ask any other questions, to quickly type away. We don't have very long left to do that. But Nowsheen, is there anything you wanted to say to us in these closing few minutes?
Yeah, I would like to convey a message, especially to early career researchers and postgraduate students. I would like to say to them that if you want to go ahead in your career, it's very important to plan ahead. Always have a personal development plan, and remember to update your personal development plan as you go along, and always give yourself deadlines. That is, if you say that I want to achieve this, or I want to improve, for example, my communication skills, set up a goal, have a vision first, set goals, make plans, and once you have made plans, assess yourself whether those plans have been successful or not, and take the required action. So the most important thing is to always have plans ahead. And this is also applicable to writing grants, to applying for grants, for example, applying for prizes, for fellowships. Always have in mind what you want to have, what you want to be where you want to see yourself in 5 years' time, and constantly review your personal development plan.
I must say, I really admire your determination. I really do, and that's extremely good advice. It really is. I think also you're doing something that you really care about, and you're doing something that you are obviously absolutely fascinated with. And I must say, I think that is also incredibly important for success, because it allows you to drive to action, doesn't it? If you're doing something that you really, really believe in.
Absolutely. So I think that if you like what you're doing, then work is not really work.
No.
So it's something that you live for, actually. So it becomes your passion, and then you're determined to make it work, to try to find solutions. And I think it's the same. It's the case for all scientists across the world. So once you set a target, you will do your best to achieve it.
Absolutely. Well, there is no doubt whatsoever that you are achieving it. And as we come to the end of our time, I wanted to thank you very, very much for your lecture, which was just a really good example of a great lecture. I really enjoyed it very much. You fielded lots and lots of diverse questions. I loved your comment that, that's a question I was expecting. I enjoyed that very much. And thank you for really educating me as well. As I said, this is not an area that I was terribly familiar with. And I've learned an awful lot. And I think that's that's how you know it's been a great lecture. So thank you very much indeed. As we finish today, I also wanted to let everybody know that the next public lecture is the Rosalind Franklin lecture. It's going to be given by Suzanne Imber, who is a planetary scientist from the University of Leicester. And that's going to be on the 9th of February. So having said that, again, Dr. Goonoo, I just want to thank you for being our rising star and the first recipient of this prize. And you've set the bar very high. So thank you very much indeed. Thank you.
Thank you.